Welcome to the Picture Language Seminar. We have a set of very interesting talks lined up, ranging from quantum information to mathematics to physics, back to mathematics. So today we're really happy to have Kaifeng Bu. Kaifeng is supposed to be a postdoc at Harvard University, but he's currently in Hangzhou visiting Tsinghua University because of visa problems, not yet back in Cambridge. But Kaifeng is doing very interesting work and will tell us about complexity of neural networks. Kaifeng, why don't you share your screen?
Okay, thank you, Arthur. Let me share my screen. Okay, can you see my screen?
Yes.
Okay, thanks, Arthur, for the introduction. Today, I will talk about the complexity of neural networks based on our recent two papers. Here is the reference of our recent two papers. And this is the outline of today's talk. In the first part, I will focus on the complexity of functions. I will introduce the topological entropy from dynamic system and talk about the depth-wise trade-off for classical neural networks based on topological entropy. In the second part, I will talk about the complexity of function class. And I will introduce some basic knowledge about Riemann complexity and show the Riemann complexity of quantum circuits. And in the last part, I will make a summary of this talk and list some further direction I'm interested in or I'm working on with. Okay, so before introducing our result, I would like to introduce introduce some basic knowledge about neural networks. Here is an example of a neural network, which is also called a feed-forward neural network. Okay, so in this graph, okay, so the blue node is called the input neuron. So this layer is called the input layer, and the black node is called the hidden neuron. So these two layers are called the hidden layers, and the green node is called the output neuron. So this layer is called the output layer, and each edge in this graph is a weight. So so the weights between two layers can be formed as weight matrices. Weight matrix. Okay, and for the hidden neuron, there is a activation function sigma. Usually, this function sigma is a real-valued function, and sigma is usually non-linear. So the hidden neuron is just to do such computation. Okay, so formally we can we can write the we can express the neural network by this formula in mathematics. Okay, so here the x is the input of this neural networks. The w is the weight matrices of between each layer, and the fx is the output of the neural networks. So and besides the number of hidden neurons plus the output layer is called the depth of the neural networks. For example, the depth of this neural network is 3, and the maximum number of neurons in the layers is called the width of the neural network. So for each for this neural network, the width is 6. Okay, and here I give 2 examples of activation functions which are widely used in machine learning. The first one is called the sigmoid function. The second one is called ReLU. The sigmoid function is defined as 1 over 1 plus e to the power of minus x, and this is a picture for the sigmoid function. And the ReLU is defined as the maximization between 0 and x. So this is the picture for the ReLU activation function. So this is a basic knowledge about the classical neural networks. And the classical neural network can be simply regarded as some parameterized functions. And there is a famous theorem in classical neural network called the universal approximation theorem. Roughly speaking, it tells us that any continuous function on a bounded domain can be approximated by a depth-2 neural networks with a sigmoid activation function. But this statement, requires requires that the neural network could have arbitrarily large Ys. But usually, this is impractical in real life, because in real life the resource is limited. So we are usually interested in the case that the Ys of the neural network is bounded. So when if the Ys of the classical neural network is bounded, then the depth could be larger than 2, right? So there's some kind of depth-wise trade-offs. And in mathematically, usually, if we want to get such depth-wise trade-off, we needed to introduce the notions of complexity of functions. So the first, let us go to the first part, the complexity of a function, which means we need to quantify how complicated a function is. There are several measures of complexity of functions. For example, the number of oscillations, the number of fluctomes, the number of linear regions. And here I list several literatures on the measures of complexity. There may be many other literature on this topic I'm less familiar with. But in today's talk, I will focus on the topological entropy from dynamic system as a measure of complexity for functions. Okay. So what is topological entropy? What's the definition of topological entropy? In fact, there are several equivalent definition of topological entropy. Here we take the one introduced by Alder, Kohlheim, and Michelangelo, introduced in 1965. Okay, so let X be a compact Hausdorff space. Because here we only consider about the one-dimensional dynamic system. You can simply think X is a closed interval. And let F be a continuous map from X to X. Okay, and let the A be an open cover of X. Open cover means each element in A is an open subset of X, and their union is X. And by the basic knowledge, we know if X, because X is compact, so there must be a finite subcover from of A that also covers X. So we can define the quantity NA to be the minimal cardinality of the subcover from A. So this is the definition of the quantity NA. And given a set of given n open covers A1, A2, A3 to AN of X, we can define the intersection of these n open covers as follows, right? And because n is finite, then this intersection is also an open cover of X. Okay. So now, given an open cover A, and given a continuous map F from X to X, then we can define the pre-image of an open cover as follows. Because F is continuous, then it's easy to see this pre-image is also an open cover. So then we have then we can get a series of open covers from the open cover A and the function F. Then we can define the corresponding intersection of these open covers. Let me take a simple example. So for example, we take the open cover A, which only has two elements, A0 and A1, right? Then the intersection, ANF could be defined as Ni0 intersects F minus 1 Ni1 to F minus N minus 1 Ai N minus 1. And the label I0, I1 to In minus 1 could only take a value from 0 and 1, right? So which means this vector is just a bit string of length n. Okay, so roughly speaking, we can encode each point of x in the each point x as a bit string I0, I1 to In minus 1 if x belongs to this intersection. This encoding is not perfect because the point could be belongs to different intersections. But you can think simply think this is some kind of encoding, and then this will give some interpretation of this quantity. So what does this quantity mean? This quantity means the minimum number of words of length n that we need to encode the points of x according to the first n minus 1 iteration of the function f. Okay, so this is just some simple interpretation of this quantity NAF, because we need to use this quantity to define the topological entropy. Okay, so finally we get the definition of topological entropy. Okay, here's the formal definition of topological entropy. Given a compact host of topological space X and a continuous map F from X to X, and for an open cover A, the topological entropy of F on the cover A is defined by this formula. Okay, but this definition depends on the open cover A. So if we take the supreme of all the open covers, then we can get the topological entropy of F. So this is the definition of the topological entropy. And the topological entropy could take values from 0 to infinity. Okay. Here, let me give several examples. The first example is quite simple, and the corresponding topological entropy is log to 3. And the second example is a function whose topological entropy is infinity. Because the definition of this function is a little complicated, so I don't put it here. If you are interested in it, you can find it in our paper. And the next, let me introduce a very important family in one-dimensional dynamic system called a ternary map. Ternary map TF, it has some alpha is a parameter which takes value from 0 to 2, and T alpha is a continuous map from the closed interval 0, 1 to 0, 1. And when x is less than 1/2, the function takes value alpha times x. When x larger than 1/2, then the function takes value alpha times 1 minus x. Okay, so this is the picture for the ternary map T alpha for different alphas. And this is the picture for ternary map for when we iterate the function for 4 times. Okay. And we can compute the topological entropy for the ternary map for different alphas. And we found that when alpha is less than or equal to 1, then the corresponding topological entropy is equal to 0. And when alpha is larger than 1, then the topological entropy is equal to log 2 alpha. Okay, so these are the examples of topological entropy. And after this preparation, we can show our result on the depth-wise trade-offs based on topological entropy for classical neural network. So let us go to the first result. Here, we use ReLU network. ReLU network means the activation function in this network, neural network, are all the ReLU activation function. And we use ReLU network with at most L layers and at most m nodes at per layer. This means the width of the neural network is less than or equal to m. We use this kind of ReLU network to represent one-dimensional real-valued function g, and we found the topological entropy of g is less than or equal to L times 1 plus log 2m. Okay, so this topological entropy is bounded by the multiplication of the depth times the logarithm of the width. And here, what's the definition of the function tau? Tau is defined by as this formula. The reason why we introduced the tau here is we want to restrict the function g on some closed interval, so that the tau g is a continuous map from some closed interval AB to AB, so that we can define the topological entropy, right? Because the definition of topological entropy requires a compact Hausdorff space. Okay, and here we consider ReLU network, but in fact we can replace the ReLU by other activation function, and we can get a similar result. So all the details is presented in this work. If people are interested, you can find the details in this paper. Okay, so this is the materials I would like to talk about. The part one about the complexity of functions, the depth-wise trade-offs based on topological entropy. And is there any question before I go to the second part? So if there's no question, I will move to the second part. Okay, so let me move to the second part. In the second part, let us talk about the complexity of a function class. The complexity of a function class means we want to quantify the richness of a function class.
Kaifeng, we've lost your audio.
Hi, Arthur. I cannot hear you.
We lost your connection when you started part 2.
Okay, sorry about that. I don't know why the Wi-Fi doesn't work suddenly. So sorry about that. So let me reshare my slides. Okay. So is there any problem for the any question for the first part?
No, start the second part.
Okay. Oh, sorry about that. Sorry guys, my Wi-Fi doesn't work there. So let me start the second part. So in the second part, we will talk about the complexity of a function class, which means we need to quantify the richness of a function class. And so function class just means the set of functions. For example, here the set of this is a set of functions, and each element is a parameterized functions of zeta. Here, zeta is some parameters, which takes value from some parameter space. For example, in the classical neural network, the zeta could be the parameterized matrices. And there are several well-known measures of complexity for function classes. For example, the Riemann complexity, Gaussian complexity, VC dimension, pseudo dimension, coupling number, the Parkin number, and so on. But today I will focus on the Riemann complexity. So what's the definition of Riemann complexity? So what's the definition of Riemann complexity? Sorry. Okay, so what's the definition of Riemann complexity? Let F be a set of real-valued functions, and let S be a set of M independent samples drawn according to some unknown probability distribution. Then the Riemann complexity, or the empirical Riemann complexity of F, with respect to the sample S, is defined by this formula. Well, the random variable epsilon I is the random variable. The random variable means it only takes value +1 or -1, and the probability are equal to 1/2. And based on the definition of the random complexity, it can be viewed as measuring the correlation between the random vector and the function f. Okay. And the random complexity has a lot of application. And for example, it can provide some bound on the generalization error. Okay, what is generalization error? Given a hypothesis space F and given M independent samples, where each sample is taking IID from some unknown probability distribution. Given a loss function little l, then we can define the expected error, capital LF. And the goal of learning task is to find some hypothesis function f from the hypothesis space to minimize this expected error. But unfortunately, we don't know the probability distribution D, and we don't have access to all the samples from this space. And what do we have? We only have access to the M samples. So one strategy is to define the empirical error L hat F based on these samples. And we try to minimize the empirical error by the hypothesis function from the hypothesis space there. So the difference between the expected error and the empirical error is called the generalization error. And the generalization error determines the performance of the hypothesis function on the data which we haven't seen before, right? So this generalization error is an important quantity, and it has been proved that Riemann capacity can provide an upper bound on the generalization error. Okay, if you are interested in the exact formula of this statement, you can find it in this paper. And the Riemann capacity of classical neural networks has attracted lots of attention, and there are lots of research on this topic. But less is known on the Riemann capacity of quantum circuit. To talk about the Riemann capacity of quantum circuits, first we need to define the functions generated by quantum circuit. Here we define the function generated by quantum circuits by this formula. So given a sample x, then we encode x to be a quantum state plus x. Then we apply a quantum circuit. This quantum circuit could be some parameterized quantum circuit. For example, quantum neural network, variational quantum circuits. After this quantum circuit, we can measure in observable H is measured. Then the FCX is just the expected measurement outcome of the circuit. For example, X is a picture of a dog or a cat, which is encoded as x. And then we apply parameterized quantum circuit C zeta. Here the zeta are the parameters we would like to train. And after the circuit, we apply we will measure an observable H. Then if the expected outcome is larger than 0, then we see the input picture is a cat. Otherwise, we see the input picture is a dog, right? So this is the way we used to define the function or function class generated by quantum circuit. So give a set of quantum circuits C, we can define the corresponding function class F circle C by this way. Of course, we need to fix the observable H. And then we can talk about the Riemann capacity of this function class. Okay, so the goal is to show the dependence. The goal of our work is to try to show the dependence of the Riemann capacity of quantum circuits on the structural parameters of the quantum circuit, such as the depth of the quantum circuit, the width of the quantum circuit, and the amount of resource in the circuit. Okay, so the goal is to bound the Riemann capacity of quantum circuits by the amount of resource, depth, and the width of quantum circuits. Okay, to realize the goal, the first thing we need to do is to quantify the amount of resource, right? So we need to find some way to quantify the resource. Okay, luckily there's a widely used framework to quantify the amount of resource, which is known as resource theory. So here I give an overview of resource theory. There are three basic elements in the resource theory. The first one is the set of free state. The free state means the state that carry no resource. And the states which are not free are called the resource state. For example, in the resource theory of entanglement, the separable state are the free state, and the entangled state are the resource state in this resource theory. The second object are the free operations, which means the quantum operations that are considered to be easy. Okay, and usually the free operations will map free state to free state, and the quantum operations which are not free is called the resource operations. Okay, then let me introduce the third object, which is the quantify or resource monotone or resource measure, which is the function that measures how much resource in the quantum state of quantum operations. right? So this is the basic framework of quantum resource theory. And here we consider a specific resource called magic. To define the resource theory magic, we first need to specify the set of free state, the set of free operations. And so first, let us define the Pauli operators. Here we consider the Pauli operators on n qubit system, which means the tensor product of n Pauli matrices with a plus minus sign. Then let us define the stabilized state, which are the simultaneously plus one eigenstate of 2 to the n commuting Pauli operators. And the set of stabilized state or the converse combination of the stabilized state are defined to be the free state in the resource theory of magic. Okay. Then let us define the Clifford unitary, which are the unitaries that map Pauli operators to Pauli operators, which are the free operations in this resource theory. Okay, now in the resource theory of magic, we have already defined the free states, the free operations. Now we need to define the resource measures to codify how much resource in the state or in the channels. Here we focus on the channels, so we need to codify the amount of magic in quantum channels. How can we do that? Here we first express each quantum channel in the Pauli basis. So we get some representation matrix of the quantum channel in the Pauli basis. We call it M phi, and this is the definition of the representation matrix M phi, right? So here Px and Pz is are Pauli operators. And then let us define the PQ group norm. So give a real matrix M, we can define the PQ group norm as follows. So first we define the LP norm of the ith vector, then we define the LQ norm of the LQ norm, so that we get the PQ group norm. Okay, PQ could be any number larger than 0. Okay, so here we take the resource measure of magic just by taking the PQ group norm of the representation matrix of quantum channel. Okay, why this PQ group norm could be regarded as some resource measure of magic? Because we prove that for a unitary channel, the PQ could satisfy the PQ group norm satisfy the following properties, such as the phasefulness, the invariance on the Clifford unitaries, convexity, or the multiplicity on the tensor product. So these properties guarantee that the PQ group norm can be used, the PQ group norm of the representation matrix can be used as a resource measure. Okay, here we give the definition of the resource. We define the resource measure for single quantum channel, but because we consider the depth L quantum circuit, so we need to generalize this resource measure for depth L quantum circuit. And in our work, we express the each depth L quantum circuit as a vector CL, and each entry of this vector is a quantum channel phi I, corresponding to the ith layer. So the ith layer is a quantum channel phi I, which map from ni minus 1 qubits to ni qubits. So this is a picture to show the structure of depth L quantum circuit. Okay. And now we can define the set of quantum circuits with fixed depth L and fixed Weiss vector N as this one. Okay, so this is just the set of quantum circuits with fixed depths and fixed Weiss. And now we are ready to define the resource measure for depth L quantum circuit. How can we do that? The first method is to define the average amount of magic of the layers of the quantum circuit, which means we take the PQ group norm of each layer, and then we take the arithmetic mean. Okay, then we get a resource measure for the depth L quantum circuit. So this is just the arithmetic mean. If we can define the arithmetic mean, then similarly we can also define the geometric mean. which means we take the PQ group norm for each layer, and we take multiplicated them together. Okay, and by the GM AM inequality, you can get a very get a relationship between these two measures directly, right? Okay, and so now we can define the set of quantum circuits with bounded depths, bounded width, and bounded resource as this one. Similarly, we can replace by the resource measure by the other one. Okay, so what we want to do is to quantify the to study the Riemann capacity of the function class generated by this kind of quantum circuits. And here, this is a picture of the to demonstrate the representation matrix of quantum channels of a depth of each layer for a depth L quantum circuit. Okay, so after this preparation, let me show our result on the which give an upper bound of the upper bound on the Riemann capacity by the amount of resource, depth, and width. So given M independent samples S, then the Riemann capacity satisfy the following bound. For P larger than 1, less than 2, then the Riemann capacity of this kind of quantum circuits is less than equal to nu to the power of L. Remember, nu is the amount of resource. L is the depth of the quantum circuit. Times 4 to the power of L1 norm of n. L1 norm is defined to be the summation of n1 to nl times maximization of 1 over p star and 1 over q. P star is the conjugate of p, which means 1 over p plus 1 over p star is equal to 1. Okay, and times square root of minimum of p star and 8 n0. N0 is the number of qubits of the input quantum state, and over square root of m. M is the number of samples, and the times some quantity kpsh. Kpsh is some quantity only depends on the observable h and the samples per xi. Okay, so so we have this bound for p equal to p larger than 1 and less than 2, and we can choose a suitable p and q to reduce the exponential dependence on the L1 norm of Weiss vector to, for example, polynomial dependence or to some constant, right? Because we can choose p equal to 1, then 1 over p star is equal to 0, and we can choose q equal to infinity, then 1 over q is equal to 0. So this quantity is become 1. So which means we can choose suitable p and q to reduce the exponential dependence on the L1 norm of exponential dependence on the L1 norm of Weiss vector to polynomial dependence or to some constant dependence. And for p larger than 2 or larger than 2, then we can also get some bound on the Riemann capacity. And the bound is similar to the previous one. Okay. And of course, we can replace the new PQ, the resource measure new PQ by the other one, mu PQ. And we can get a similar result. And all the detail is presented in this work. Okay. Okay, this is all the material I would like to talk about today. And now let me make a summary of this talk. So first, we introduced topological entropy from dynamic system as a measure of complexity of neural networks. Then we obtain some depth-wise trade-off relationships for the classical neural networks based on the topological entropy. Second, we introduced the Riemann capacity of quantum circuits and get some bound by the amount of magic depth and the width of the quantum circuits. Okay. Okay, and here I listed some further direction on this topic. First, can we generalize? Can we define the topological entropy for quantum neural networks, and get some depth-wise trade-off for the quantum neural networks? Okay, similar to the case for classical neural network. Second, can we generalize the results about the Riemann capacity to other measures like VC dimension, pseudo dimension, or Cavalier number, and so on? Okay, so before the end of the talk, I would like to thank my collaborators, that's Zheng Kou, Lu Li, Qin Xianlong, and Yaobo Zhang for their hardworking and fruitful discussion. And here's two reference for the material in this talk. And there are also several other works in preparation on this topic, which I think we will put it on, post it online in the coming 2 or 3 weeks. And besides, I would like to thank Arthur, Zhe Wei, and Professor Wu for their help and support during the COVID-19 pandemic. And also would like to thank Yale Mathematical Science Center for the financial support during my visit. So that is all for my talk. Thank you for your attention.
Well, thank you very much for a beautiful talk, Kaifeng. This is interesting work, and you went through it very quickly, so I'm sure there are a lot of questions.
Yeah, sorry, because of the Wi-Fi problem, so I dropped out in the talk. So do you have any question?
Can you apply your bounds to some quantum experiment?
Well, that's a good question. And in fact, our bound, the bound on, if you can get a bound on the Riemann capacity, then it will provide some bound on the samples. Provide samples you need to get the precision on the generalization error. So if we, so usually, let me go back to the definition of Riemann capacity. So usually, if you get the bound of your Riemann capacity like this form, then if you want the generalization error is less than epsilon, which means that the sample should be taken from like c square or epsilon. Oh, sorry, it should be c square epsilon square. So the Riemann capacity will give some upbound on the samples you need to get the desired generalization error you would like to have, right? Because you would like your algorithm is good enough such that the empirical error you get is close to the expected error. So in fact, the Riemann capacity will give some bound on the sample capacity. This is the application in the machine learning. I don't know if it has application in the like quantum experiment.
May I ask a question?
Okay.
Could you restate your result, the second result, in natural language?
What do you mean in natural language?
What's the implication for general audience?
Well, so first what we want to say is that we want to show this complexity, how well the complexity depends on the structural parameters, right? Because when you have a set of quantum circuits, you will have the structures like the parameters you can take. And then we want to see how these parameters determines the Riemann capacity.
Yeah, but what's how to say? What's the
So,
dependence
for example,
on...
so as I said before, random complexity can provide a sample of the upper bound on the sample complexity.
Yeah,
the
I know.
sample you need
I mean the dependence on like width, depth, and the magic. You have those formulas, but these formulas, but I mean,
so which means that when the amount of the resource will give you bound of the give the bound of this complexity.
is this bound
So
high?
it's I'm not quite sure because we also get some unbound when we in fact in our work we treated this depth cell quantum circuit in two different ways. First, we treat it as depth cell quantum circuit with fixed structure. Second, we just treated the depth cell quantum circuit as a single quantum channel, and we get two different bounds. But we don't know which bound is close. It is much close.
Okay. What if we fix the depth and width and allow the non-Clifford gate? In this case, is this bound polynomial?
Yes, I think so because the depth is fixed. So the depth is the power of it's the power. So which means the
no. I mean for depth also scale as polynomial then.
Let me think. Because this is the average value, then you should say it's the average value. When you take the average value of all the layers, is this value is still like constant? If no, it should not be because if you scale the depth, then this bound should be some polynomial of n, and even if the v is fixed, it is still like exponential. But because the L, let me see, because the mu is defined to be this one, the number of well, I need to think it. We can talk about it directly after the talk.
My impression is that because you are using a greater than 0 or less than 0 as the indicator to do the classification, we know that if you only have sin theta function, you can have infinity VC dimension, right? VC dimension is related to this complexity, right? So
yeah. In fact, they are equivalent up to some constant, right?
Yeah. So my impression is that maybe when depth scale with the system size is not polynomial.
Yes, but it depends what's the circuit, what's the gate you used in the.
Yeah, I mean generic quantum gate. Local gate.
I don't think so because it will. I think it will goes exponentially with the depth.
Okay.
Because we have another bound by this one. This one is much clearer because we multiply the resource measure, the amount directly, and you have more. If you have more non-Clifford gate, then the measure will go through with the amount of like how if this is the resource magic for each gate, then it will go through like this way. If my memory is correct, it will go exponentially for this one. But for this one, I'm not quite sure.
So intuitively, if we have the sample complexity grows very quickly with the amount of magic, could I regard this as a take-home message?
Yeah.
Okay, thank you.
So maybe Dax has some comment.
Hi. Yeah, well, I guess this you're talking about the dependence on the depth and the magic, right?
Mhm.
Yeah, I guess so. So the bounds give you a way to, I mean, give you an upper bound for the Rademacher complexity in terms of these structural parameters. But I don't think they are necessarily tight because there's some approximation in the proof. Yeah, I'm not sure. Do you have any other questions?
I was wondering, is this bond efficient in terms of the size of the circuit?
So we're not well, it grows exponentially. So in that sense, it's not efficient. But
Okay.
I think I guess the part we're not clear about yet is the like how tight is the bound, how tight the bounds are. So that really, I think yeah, you have to, I guess we have to examine the proof to see the approximations used.
Okay, thank you.
Yeah, sure.
So are there any other questions? Any comments or suggestions? Well, if not, I'd like to thank Kaifeng for a really interesting talk. And it's good to see work while it's being developed. And we look forward to the next step. So thank you very much. See you again next week. Bye-bye.
Yes. Bye-bye.
Yeah.
See you.